So hello once again. So new day, new topic. This time we're looking at integration, mathematical integration. So we're first of all going to consider it as the exact opposite, the reverse process of what we looked at last chapter, differentiation. Integration undoes differentiation. They're both inverse processes, just as you have add and subtract, you have multiply and divide. So let's have a look. And first of all, of course, we're going to do a couple of warm-up questions. By a couple, I actually mean 3 this time. So here they are. So once again, pause the video now, have a go at them by writing them down. If you can print this off, even better. Complete them, have a go, then use the video to check your solutions. So let's have a look at these together now. So question 1, like I've said, we need to consider differentiation as the inverse of integration, and so vice versa as well. So first of all, let's consider what we need to do to differentiate the function x to the power n in 2 steps. So like we mentioned last time in chapter 12, first of all we need to bring the power n to the front. So we need to multiply the term by the power. After we do that, we then take the power of x and reduce it by 1. So we consider it as 2 steps here. So first of all, multiplying the term by the power of x, then reducing that power of x, or the variable, by 1. So imagine this as a function machine, like you may have seen at GCSE, for example in solving equations. We can then undo it by reversing each step in the reverse order. So if we were to take this function which we differentiated and undid it, which is what integration is, the opposite of reducing the power of x by 1 would be to increase the power of x by 1. And the final method in this box, instead of multiplying, we'd do dividing the term by the new power of x. So opposite order, opposite steps. So that's how, in a nutshell, we can integrate functions where we have just a power of x to consider. So just taking this a bit more forward, question 2, imagine we've got these gradient functions f dashed of x. Imagine what the possible original f of x may have been before it was differentiated. So if we just think about question 1, the reverse step, and apply this now. So first all we need to do is increase the power of x by 1, then divide by that new power of x. So for the first one, what we need to do is increase this power of x by 1. So 12x becomes 12x squared, and then divide by that new power. So in other words, the original function f of x may have been 12 divided by 2, which is 6 lots of x squared. Now if you're wondering what I mean by possible f of x, why it couldn't just be 6x squared and nothing else, then hold on, later in this video I'll come to that and explain in a bit more detail. Part B, same idea. So f of x could be where we just take this derivative, increase the power of x by 1, so squared becomes cubed, and divide through by that new power, which would give us 4x cubed. And for part C, again, the same idea. F of x may have just been where we took this expression here, increase the power of x by 1, so we have 12x to the 4, then divide through by 4, which would give us 3x to the power 4. So all we're doing here is undoing differentiation, applying the opposite steps. This is, in its simplest form, what integration is. The last one, a bit of probability recap for you. So a Venn diagram we've got here shows 3 events as a charity fundraiser: archery, raffle and a fun run. The probability that somebody takes part in archery or raffle is 0.6. So first we need to find the values of x and y. So we've been given a big tip here. So what we've been told first of all is the chance that they take part in archery or the raffle is 0.6. So the numbers in the archery bubble, A, added to the numbers in the R bubble, should add up to 0.6. So that's the first thing we can write down. So 0.2 plus 0.25 plus x needs to add up to 0.6. So therefore, that's a fairly simple equation to solve. Therefore, x must be 0.15. The value of y, well, we can now use the concept that the sum of all probabilities for any one closed event needs to add up to 1. So this event being archery or raffle or fun run or none. So now we've got every single probability here. We know that what x is, so from this we can work out what y must be. So 0.2 plus 0.25 plus what x was. We've worked out what x is. We know now that x is 0.15. Plus, of course, don't forget the 0.1 on the outside. Plus y must add up to 1. So if we add up all these decimals together, so 0.2 plus 0.25 plus 0.15 and so on, that'll get us to 0.7. So 0.7 plus y must equal 1. Therefore, y must be 1 minus 0.7, which is 0.3. Whoops, sorry, that isn't part B, that's still part of part A. Part B is where we need to show that events R and F are not independent. So what we need to do for this here is first of all consider what the probability of R multiplied by the probability of F would be. So probability of R would be 0.25 plus x, so 0.25 plus x is 0.4, multiplied by the probability that they pick the fun run, which is x plus y, and x plus y is 0.15 plus 0.3, that's 0.45. Multiply these two together, we'd get 0.18. Now, if two events are independent, the probability of one multiplied by the probability of the other will always be the same as the probability of the intersection. So it should be the same as probability of R and F combined. If it is the same, then the events are independent. If they're not the same, they're not independent. So the probability of R and F together, that just is the intersection, which is where R and F intersect. Now they intersect where this x is, and so the probability of R and F is x, and x we've worked out is 0.15. So 0.18 is not the same as 0.15, and this therefore shows us that the events are not independent. Events are not independent. And then we've done the warm-up. Okay, so basic introduction to integration. So as I've mentioned before, we can think of integration as the reverse process to differentiation. So first of all, before integrating anything too complicated, we're just going to have a look at differentiating simple functions and then trying to integrate them back again. So this was going to be a student activity where I wanted you to do this in pairs. So if you're watching this video, you probably have to do this solo, or if you're really, really keen, I suppose you could WhatsApp or God knows what is it you use? I forget, I'm not very up on social media. Anyway, you could do a video conference. Nothing more fun than doing a maths video conferences with your friends, and just work these out in pairs or even small teams. I imagine you're not going to be doing that, so let's just do this individually in these circumstances. So first of all, we're going to take these functions, we're going to differentiate here, and then we're going to reintegrate them and put the answers back here and compare off what we started with to what we end up with. To try and explain what I mean, I'll do one for you. So imagine differentiating y equals 2x. So when we differentiate, we drop the power of x by 1. So x to the power 1 becomes x to the power 0, which basically just ceases to exist. And then we're just left with the 2. So the derivative would be 2. Then follow this instruction in red, increase the power of x in each term by 1, then divide each term by this new power. And so this you need to imagine as being x to the power 0. So take the 0 up to a 1, so this will become y equals just 2x to the power 1. So what we end up with is exactly the same as what we've got here, and so we can see that we get the same and they match. So I want you to try this for 1 part B, 2A and B, and the blue ones at the end. So if you want to pause the video and have a quick go at that, it shouldn't take you too long. Then we'll compare our answers, and then I'll try and talk you through what the whole point of this is. Okay, so pause now if you want to. And let's have a look at what you should have got. Okay, so the yellow ones should have both differentiated to 2. However, when you integrate them back, you should get 2x each time. So this one matches to the original function. 1b doesn't. For the green ones, the first one 2a matches, x squared and x squared. The second one doesn't match. And the same again for the blue. 4x cubed minus x is the same function, whereas down here we've missed the minus 1. So the important key point here is that when you differentiate a constant term, for example a minus 5 or a pi or a minus 1 or whatever, when you differentiate a number, the constant term just vanishes. And so in terms of these answers here, which I wanted you to fill in, when you compare them, which antiderivatives, that's just a technical term for when you integrate a derivative. Antiderivative means opposite. So one way you could think of an integral as being an antiderivative, it's the reverse process. So which antiderivatives, these on the bottom row, match? Well, like I just mentioned, 1a, 2a and 3a match, but 1b, 2b and 3b don't match. So from the ones that do not match, the b ones, what's missing from the antiderivative, these ones here, which was present in the original function? So as you can see, this minus 5 just hasn't been accounted for. Pi is a constant, albeit a very famous constant. It's not accounted for down here. And the minus 1 just vanishes, and we never got back to it in this final line. So just putting that into words here. So what I'm trying to get at, what I'm digging at, is what we need to consider when we do the opposite of differentiate, when we integrate. What we need to consider is that in the original function, which you're trying to find, there might have been a constant term. There might not have been. Like here, there was no constant term, but there may have been. And so what we need to do, we need to account for that possibility by including what's called a constant of integration when we integrate. Sometimes a constant of integration will be 0. In other words, sometimes there won't be a constant of integration you need to consider. But just in case, you need to add in a constant of integration. And what we call this constant of integration, we call this almost always C. C stands for the constant of integration. So in general, just to get this point across, if you've got a derivative function, gradient function, dy by dx equals x to the power n, then the original function, y, we increase the power of x by 1, and we divide through by this new power. And we also include the constant of integration just in case. So always do plus c, where c equals the constant of integration. Now the second line is exactly the same thing, but I'm just writing this in a different format. So if in function format, f dashed of x is how you'd write the derivative, then the original function would be f of x, which is 1 over n plus 1, x to the power n plus 1 plus c. And it also works if you have a constant term before the variable, for example, the constant term k. So if the gradient function is kxn, then in almost exactly the same way, the original function y will be 1 over n plus 1, then kx to the power n plus 1 plus c. And if you want to, you could write this as y equals kx. Sorry, my mistake. Not kx, but just k over n plus 1 x to the power n plus 1 plus c. So instead of having the 1 on the numerator, we just have a k here. And in a function notation, then we'd just say that f of x equals k over n plus 1 x to the n plus 1 plus c. So these are very powerful general results which we'll see time and time again in year 12 and in year 13. So let's just do a few examples just to practice integrating some basic functions. So first of all, imagine we've got dy by dx equals x to the power 5. The original function, y, would be x to the 6 divide by the new power plus c. So we could leave it like that, that would be absolutely fine, or you could just write it as a sixth of x to the power 6 plus c. This one here, dy by dx equals minus 3x to the power minus 4. So again, just follow the same robotic procedure. What we do is we just take this, increase the power of x by 1, so the minus 4 becomes a minus 3, and divide through by this new power. So minus 3 is the power, divide through by minus 3. Minus 3 divided by minus 3 cancels nicely, and just gives us 1, so we're just left with x to the power minus 3 plus c. And I almost forgot to include the c here. This one is not in index form. So first of all, I'd rewrite this as dy by dx equals x to the power minus 3. Therefore, if we integrate this, increase the power, minus 3 goes to minus 2. And we're going to divide through by minus 2, and then plus c. If we divide through by minus 2, that's the same as saying it's minus a half x to the power minus 2, and then plus c. Lastly, this one, again, I'd write this in index form. So we have x over x to the power 3 over 2. Remember, square root means to the power half. So cubed, then power a half. 3 times a half gives us 3 over 2. When we're dividing with indices, remember, we do the top power subtract the bottom power. So 1 minus 3 over 2 would be x to the power minus a half. Therefore, when we integrate this, we have x to the power minus a half. Increase that power by 1. Minus a half plus 1 gives us a half. Divide through by this new power. Then add on the constant of integration. If we divide through by a half, dividing by a half is the same as multiplying by 2. So our final simplified answer is that y, the original function, must be 2x to the power half plus c. And that's our answers done. So remember, just treat it as a procedure. Keep it safe, keep it simple. Don't try and skip ahead at this stage. With enough practice, these will become second nature, so you don't need to do quite as much working. But for now, my definite advice would be to follow this procedure again and again until it becomes assimilated firmly in your head. Afterwards, it'll then become, as I say, second nature. Okay, so just before we finish, a couple of slightly trickier ones, but no different to what we've seen before. We just take it term by term. So here, what we're going to do is we're going to integrate each term individually. So the original function, whoops, don't want that to be in red. There we go. So y, increase the power here. Any constant, we just add an x at the end. This one, increase the power by 1. 3 becomes 4. Divide 3 by that new power. This one here, doesn't matter if it's too messy to begin with, you can always neaten it up in the next step. Increase the minus 5 by 1, make it a minus 4. And then divide through by minus 4. Square root means power half, so increase that power half by 1. We then get 2x to the 3 halves, divided by that new power, which is 3/2, plus c. Now this would be pretty unforgivable to leave it in this form in an exam, but we can just neaten this up ourselves. So what we're going to do here is say that's 3x minus 7/4 x to the power 4. 4/5 divided by minus 4. This 4 and the minus 4 would cancel to 1, and the minus sign would make it minus 1/5. So we'd have minus 1/5 x to the power minus 4. This term here, 2 divided by 3/2. If you divide it by a fraction, remember, keep, change, flip. So think of this as 2 times 2/3, which would give us 4/3. And again, use your calculator just to be absolutely positive. X to the power 3/2, and of course, plus c, lest we forget. Really important for these. Always remember the constant of integration, unless you want to lose marks time and time again. Finally, part B. What I'd suggest we do here is to expand this out so we can treat it then term by term afterwards. So we square the first term, square root of x squared, just gives us back the x, double the product, square root of x multiplied by minus 1 is minus root x, double that gives us minus 2 lots of root x. Remember, root x is x to the half. Then minus 1 times minus 1 gives us plus 1. So now if we integrate this, increase the power of x to the power 1 to x to the power 2, and divide by that power. This one here, half plus 1 gives us 3/2, and divide through by that new power. As I say, if it's a constant term, just stick an x on the end. So 1 becomes 1x, which is just x. Neaten it up. We have half x squared. 2 divided by 3/2, same as this here. The only difference is now it's a negative 4/3. Then we have x to the power 3/2 plus x. And look what I've done there. I forgot my own advice. Always remember plus c. It's easily done. That's no excuse though for me. It's no excuse for you either. So, take-home points for today. Integration is the opposite of differentiation. Treat it as a robotic procedure. You need to do that until you can appreciate the absolute beauty of it, and it is, I promise you, beautiful. It's exciting as well. And remember, always include the positive of integration at the end. Take it term by term in the same way you would differentiation, and you shouldn't go too far wrong. However, what you do need to do, as always, is to practice these things, otherwise you'll get absolutely nowhere. So on that note, here are the suggested exercises, page 289 to 290, exercise 13a in your pure mathematics algebra book. So crack on, have fun. Any problems, please do email me or leave me a comment in the comment section. Do work as well as you can, and I'll see you in the next video. Do keep in touch, and please, above all else, keep safe. Thanks for listening, and see you again next time.